Hi everyone, my name is Milliner, and today I'm going to be talking about how we've been developing probabilistic hazard models for strikes and faults using remote sensing imagery to measure the total fault displacement. So to measure fault displacement from remote sensing images, we use an image correlation technique. This measures the amount of surface motion by tracking the shifting of features from images acquired before and after an earthquake. So the correlation process works by using a sliding window across the image to try and find and match the same spectral pattern of pixels between the before and after images. And so this correlation technique spits out motion in the east-west and north-south direction, so it constrains primarily the horizontal direction, but we've also now employed some more recent techniques that can measure the full 3D surface motion. So once we have the surface motion measured, we can then calculate the fault displacement across the rupture. So this is a result here of the horizontal surface motion projected in the east-west direction for the 1999 97.5 Izmir earthquake that occurred in Turkey. We then estimate the amount of fault displacement across the rupture using these very long profiles oriented across the surface rupture. And so you can see here, this illustrates these are the profiles. It shows the variation of displacement shown by the red line across the fault from left to right. And so we calculate the fault displacement by fitting these error functions, as that's shown illustrated by these black lines. And so this captures the magnitude of this kind of step or the differential surface motion across the fault. And so these profiles capture both the on-fault and the off-fault shear across the entire width of the surface rupture. So we define our measurements as being the total fault displacement. And so this is what differentiates these observations from those measured in the field primarily. And so we can repeat this procedure and measure the total fault displacement along the rupture, and we get these long fault subprofiles. So we applied this technique to 21 earthquakes that range in magnitude from 6 to 7.9 that have occurred between 1992 and 2023, as we're shown here on the left for all these different events. So from these surface deformation maps, we then measure the total fault displacements, which is shown here on the right. And so these are all the slip profiles for all of these different earthquakes. I've just arbitrarily separated them in the vertical direction just so you can see how they all compare at the same scale. So in total, we measured 2,600 fault displacement measurements with a long fault sampling density ranging from hundreds of meters to 4 or 5 kilometers. And because these earthquakes have occurred at different times, require us to use a range of different images from acquired different sensors. So we're using both optical and radar data from both satellites and the aerial platforms. So if you're interested in using these data, they're actually now publicly available in the SAGE special issue and all these surface deformation maps, and the total fault displacement data can be retrieved freely from the Zenodo data repository. So we can compare our fault displacement measurements derived from the remote sensing imagery to those measured in the field. That's what's shown by this figure. So the blue dots are fault displacement observations from the remote sensing data, and the magenta are from field surveys for a number of different events, plotted as the distance along the fault, and the y-axis shows the fault displacement. And so the data shown in the blue circles here form the basis for concerning our empirical ergodic fault displacement models, although I'm not showing all of the events here. And so this equation here describes how the mean amplitude of the fault displacement varies as a function of the moment magnitude in a bilinear manner and as a function of the distance along the rupture according to a symmetrical elliptical function. So we can see the fault displacement and from the field and the remote sensing data differ in two important ways. The first is that the geodetic data shown in the blue circles are systematically larger than the field observations, which is shown in the magenta. And second, there's systematically much higher long strike variability found in the field measurements compared to those found in the field observations. You can see these magenta circles are more heterogeneous. And so from this regression, we can compare how the mean displacement varies as a function of just the moment magnitude here. So that's what's shown by this blue line. And so if we can then compare this displacement magnitude regression, which is shown by the red line for the field observations. And so there's a couple of important things to note here. The first is that as expected, the geodetic based relation predicts systematically larger fault displacement as a function of magnitude, because we're measuring the total fault displacement. The other important thing to notice, that the slopes are shallower too for this blue line for the geodetic data, and the uncertainty bands are much narrower for our observations compared to the field observations. And so just to quickly summarize and recap, we use a range of remote sensing images to measure the total fault displacement for 21 historical strikes of earthquakes. We've used these data to develop some probabilistic models for describing how displacement is expected to vary as a function of distance along the fault and as a function of magnitude. And there's some important differences when we compare those to the field-based observations. And if you want to try and find these data and results, we have a study published in EERI, and we're now working on trying to publish the probabilistic models. So I think I'll leave it there, and I'll thank you for your attention.